Well, good evening. My name is Mujisha Martin. Registration number 2021 BIT 091PS. My project I used depth first search algorithm to find. I wanted to create a short path finder to find the shortest path between the two nodes. And I used different data structures in my project, whereby I used arrays, objects, and lists. With the objects, an object is one thing that I used that will store my graph adjacency. And here I mean this is a town and its neighbor node. For instance, we can have towns like A, B, and C, whereby we can find that town A has its neighbor nodes as B and C, and B can have its neighbor nodes as A, D, and E, like that. As in, the next town that is near the current town can become a neighbor node or a neighbor town. With arrays or path arrays, they are used in recording the current path that is being explored. And when it comes to lists, a list is used to store in the neighbor node. For instance, as I was telling you, if our town is A, so we have its neighbor nodes, which is like A, which is like B and C. So that B and C, which is where it is stored, it is what I will call a list, and that is where the neighbor nodes are stored. So as I'm going to show you, this project, the DFS implementation, we have the store graph, and in this store graph, this is where the adjacency or the town and its neighbor nodes are found. So we shall have our start node, and this will be like our current node. And this current node, after that, we can also maybe have like an end. Like let's say that it has started from, we are finding a path from town A, and we want to end at town, and let's say like at town G. So G will be our destination. That is what I call the end. So the destination node will be G. So the path tracks the nodes in the current path, which is stored in array visited, and this tracks the visited nodes to avoid loops. So the start node or the current node adds it to the path. If the current node is the destination or the end, it returns the path. I'm going to show it. If the current node is we have our different paths. We have town A, B, C, D, E, F, G, H, and I. So its neighbor nodes, the neighbor nodes of A will be B and C. The neighbor nodes of B, of town B, will be A, D, and E. For C it will be A, F, and for D it will be B and G. as I'm showing it to you here, E, it will have its neighbor nodes as B and H, and F will have its neighbor nodes as C and I. For G, it can have its neighbor nodes as D. So, well, you can maybe copy this and bring it to our browser. We shall bring it to our browser. So we shall bring it our browser. So we bring it here to our graph. So we paste it here. So let us find the test. Well, what I was trying to tell here, it will find no path. If no path is found, it returns null. For instance, if you want to find a path that is in A, that is in country A, from country A to town A, so our result will be A, which means there is no shortest path between A and A because it brings null. But if we want a town, a distance from town A to town F, well, it will bring that the shortest path from A to F, it will be from A, C, and F. So it marks the current node as visited in order to avoid the loops. So the shortest path found in the dfs function, it fetches the values from the text area and inputs the fields and validates that the start and the end nodes exist in the graph. That is, let's say, from town A to town I, as I showed you. So it will calculate it. The DFS function will call with the graph with the start node and the end node. If a path is found, formats and displays it. If no path is found, it displays an error message. So as you can see, this is our DFS function, whereby we have our graph, which is an object, and then we have the start node, the end node, and the path. All this is stored in an array visited. So if the end node is found, it returns the current path, and the path is returned, and it marks the current node as visited. So it recurs all the neighbors of the current node, and our new path will be brought in the DFS function with the graph, which is our object, and then its neighbors, and then it will bring the end node, and it will be stored in an array visited. So as I was trying to tell here, so So our function here, to find the shortest path, we have the graph input. Our input will be like our start node, as in the start node, and then the end node. So the graph will pass the input and then validate the start node and the end node. And then our DFS, and then the path will be in that object whereby we have our start node and end node. If the path is found, it will display the shortest path. Else, or if it is not found, it will display no path is found. So for instance, as I showed it to you here, if you want to find from town A to town I, for instance, it will display that from town A you will pass from town C, from town A to town C to town F, then to I. Well, this is the same. Even if our start node becomes I, and then we end with A, with our town A, still to display the same thing. As you can see, it is from I now to F, C, and finally A. So it is the vice versa of what we had. So let's get back to our code. So this, I want to show you something that will trigger. So our button element triggers the function find the shortest path when it is clicked, as I showed it to you there in our project. Well, that's all I have to present for now. In my project, finding a depth of finding the shortest path, or in my shortest path finder using DFS. Well, thanks you for your time. I really appreciate. Thank you. I remain Mugisha Martin, relation number 2021 BIT 091 PS.